Hi there and welcome to this video for Senior Physics on Electromagnetism and Electricity. In this video we're going to look at our final component on capacitors, which is the time constant. Now the time constant is basically going to involve an RC circuit or a resistor linked with a capacitor within a circuit. So let's look at the scenario that we've got set up below. Below we've got a 6-volt DC supply which goes through two parallel loops, one containing a 1000 microfarad capacitor and one carrying a resistor, 390 ohm resistor, linked to an LED. Now the LED is basically a light emitting diode. Now you can see the switch there can be positioned between 1 and 2. At the moment everything is off. However, what happens if we place the switch into position 1, as we can see here? What's likely to happen? Take a minute, pause the video and try and work out exactly what's going to happen. Okay, welcome back. So hopefully what you will have seen is that the capacitor will begin to charge. Charge will move from the negative terminal of the 6-volt DC supply and push itself onto the bottom plate of the capacitor. Now what will happen is that will charge up until it is then fully charged. At that point there'll be no net movement of charge onto the plate, which means that the 1000 microfarad capacitor will remain at around 6 volts. So the next question is, what happens then if we detach the DC supply, i.e. we switch it off and move the switch to position 2, like so. Now in this case, what do you think will happen? Pause the video now, have a think, and come back and we'll discuss the answer. Okay, so I hope you've worked out that what's going to happen is that the charge from the capacitor is basically going to flow through the bottom loop of the circuit. As it flows through the bottom loop of the circuit, the result is it will flow slowly through the resistor, and as it flows slowly through the resistor, it will then flow into the LED, causing the LED to light up. Now what we've actually generated is an RC circuit there, where the resistor and the capacitor are working together. Now if we increase the resistor, the flow of charge will decrease because it's slower to get through, and so the LED will light up for longer. It's like going back to our water barrel scenario, whereas instead of having a large hole, we're actually going to make a very, very small hole. By making a small hole, the charge will still flow out, but it'll be at a slower rate, which means it will take longer for that charge to dissipate away. Now also what happens if we increase the capacitance? If we increase the capacitance, basically what that means is we make the capacitor bigger. We make the water barrel bigger. If we have the bigger water barrel with the same resistor, although we've got the same hole, we've got a lot more charge which has been stored. So as a result, the capacitor will take longer to fully discharge, and again, the LED will light for longer. As a result, we've produced a timing circuit between the resistor and the capacitor. This is known as an RC circuit. Now, the combination of resistor to capacitor has been utilized with the idea of a time constant. Now, if you look at this circuit that we've got opposite here, we've got a voltage supply, we've got a capacitor in microfarads, a resistor in ohms, and a switch. Now, if we were basically to monitor the potential difference or the voltage across the capacitor as it charges up, we would get a graph exactly as we saw in the last video on charging. So we get this exponential graph as VC begins to increase. Now basically the time constant is given for 63% of the maximum voltage to be achieved. Now it's given the symbol tau, which is the Greek letter for T. So tau, or one time constant, is 63% of the maximum voltage. For a second time constant, it would be 63% of what is remaining. Now what is remaining is 37%. So 63% of 37%, add that to 63%, and you'll end up with approximately 86% of the total voltage. And as we move along, the time constant is always the same. What you have to then calculate is 63% of whatever's left over. Now this can be utilized in a charging circuit or a discharging circuit. Now the time constant can be calculated, or tau can be calculated, using the algorithm below in blue, where it's the resistance multiplied by the capacitance. Now, the time constant never reaches 100% because energy will be lost, and it takes approximately 5 time constants to achieve 99% of the voltage supply. So bear that in mind. So here's an example as to how we can use this. So we've got a 100 farad capacitor connected to a 10 volt battery and is used with a 2 mega ohm resistor to automatically shut off a calculator. The capacitor, when initially charged to 10 volts, discharges through the resistor whenever the buttons are not being pushed. The calculator will turn off when the capacitor voltage falls to 3.7 volts. How long will this take? So basically what we need to understand is that the capacitor voltage is going to fall from 10 volts down to 3.7, which is 6.3 volts. This is 63% of the initial voltage, and as a result will be one time constant. Remember back to what we said, one time constant is always 63% of what you're either trying to achieve or what you're starting with. So we know that tau equals RC. We know that RC is 100 times 10 to the 6. Sorry, there's an error there. It should be microfarads, not farads. It's a pretty big capacitor if it was a 100 farad capacitor in a calculator. So it's 100 microfarads, which is 1 times 10 to the negative 6. This is multiplied by the capacitance, by the resistance, of 2 times 10 to the 6 ohms. So as a result, my time constant is 200 seconds. This means that it takes 200 seconds to fall from 10 volts to 3.7 volts from a 100 microfarad capacitor running through a 2 mega ohm resistor. Okay, so basically I've put some more examples and some more exercises on the capacitance worksheet accompanying this post, and I hope you found the capacitance interesting. I hope you've also understood that the capacitors are utilized to actually fill in the gap on our AC curves, as we discussed right at the beginning of this unit. I'll come back and use the idea of this when we look at AC rectification. But for now, thanks for watching. I look forward to you joining me again.